Elementary students. Today I'd like to give you a video solutions to the study guide that was given out the day before the test. If you look at problems 1, 2, 3, and 4, the goal is to simplify the radicals. And in order to do that, we want to know the perfect square. So I'm going to write them at the top. 1 squared is 1, 2 squared 4, 3 squared 9. And if we keep going, 4 squared, 5 squared is 25. 6 squared 36, 7 squared 49, 8 squared 64, 9 squared 81, 10 squared 100, and then we can keep going. So the goal of problems 1 and 2 is to find the biggest perfect square. So 75 is 25 times 3, and then that breaks down to square root of 25 times square root of 3, and the square root of 25 is 5. So the final answer is 5 square root of 3. For problem 2, the biggest perfect square is 16. 80 is 16 times 5. That then is square root of 16 times square root of 5. And the square root of 16 is 4. So the final answer is 4 square root of 5. There isn't an alternative way of doing problem number 2. If you saw it as 4 times 20, then you could say the square root of 4 times square root of 20, which is 2 square root of 20. However, 20 also has a perfect square, so you can rewrite that as 4 times 5, and then break that up. 2 times square root of 4 times square root of 5. Again, square root of 4 is 2, so 2 times square root of 5, which finally simplifies to 4 square root of 5. Notice you get the same answer in both cases. Problem number 3, if we were to multiply, this is the square root of 16, and then the square root of 16 is 4. So the final answer for problem number 3 is 4. And the last problem, we want to rationalize the denominator. So we're going to multiply by square root of 2 over square root of 2. Multiplying across, that is square root of 6 over the square root of 4. And the square root of 4 is 2, so the final answer is square root of 6 over 2. I'm going to give another quick example. I'll call this problem 4a. Suppose I had 7 divided by the square root of 5. Well, here I would want to multiply by square root of 5 divided by square root of 5. Multiplying across, that's 7 square root of 5 over square root of 25. That simplifies the 7 square root of 5 over 5. And I'm even going to do one more example, problem 4b. Suppose we had 9 divided by the square root of 3. Well, this time I'm going to multiply by square root of 3 over square root of 3. That's going to become 9 square root of 3 over square root of 9. The square root of 9 is 3. And this last example simplifies to 3 square root of 3. So this was the original problem highlighted in blue. Then I did another example here in yellow, and the final answer was 7 square root of 5. And then I did a third example highlighted here in pink to help you with rationalizing the denominator. Let's take a look at the next set of problems, which is the Pythagorean Theorem. So the goal of these 3 problems is to use the Pythagorean Theorem, which is leg squared plus leg squared equal hypotenuse squared. Some people like to say a squared plus b squared equals c squared. Remember, c is always the hypotenuse. So in this particular problem, it would be 6 squared plus 5 squared is c squared. So 36 plus 25 is c squared. Adding that up on my calculator, I get 61 is c squared. So c is the square root of 61. There are no perfect squares in 61, therefore this is your final answer. If we look at example 6, the 15 is the hypotenuse, so I will do x squared plus 13 squared is 15 squared. Using my calculator, we get x squared plus 169 is equal to 225. We'll subtract 169 from both sides. Doing that, we'll get x squared is equal to 56. So x is the square root of 56. 56 breaks down to 4 times 14, so that's the square root of 4 times 14, and then square root of 4 times the square root of 14, which is 2 square root of 14. So the final answer for problem number 6 is 2 square root of 14. For problem number 7, the 8 is the hypotenuse. So for this problem, we'll do x squared plus parentheses 5 root 2 squared equals 8 squared. If you use your calculator to figure out 5 root 2, the quantity squared, you will get 50, and then 8 squared is 64. I'm going to show you how to get 5 root 2 squared without your calculator. So here in green, that means 5 root 2 times 5 root 2. You multiply the 5s, you get 25. You multiply the square roots, you get the square root of 4. The square root of 4 is 2, and then 25 times 2 is 50. So if you didn't use your calculator, that's how you would get 50. At this point, we're going to subtract 50 from both sides. We will get x squared is equal to 14. We take the square root of both sides, so x is 14. So the final answer to number 7 is the square root of 14. Let's take a look at problem number 8, which is an application of the Pythagorean Theorem. So the problem says a repairman leans the top of a 10-foot ladder against a stone wall, so the ladder is 10 feet. The base of the ladder is 6 feet from the wall. How tall is the wall? So we're trying to find the length of the wall. And the ladder, the diagonal line is 10 feet. So that's the ladder. And the ladder is placed 6 feet from the bottom base of the wall. So if I call the length of the wall x, I'm going to use Pythagorean Theorem. X squared plus 6 squared is equal to 10 squared. And simplifying, x squared plus 36 is 100. Subtract 36 from both sides. We'll get x squared is 64. So x is the square root of 64. Therefore, x is equal to 8 feet. Let's take a look at problem number 9. Problem number 9 is also a Pythagorean Theorem problem. The problem says the length of the two legs of a right triangle are 4 inches. I would suggest you draw your own picture for this one. So I'm going to label the right triangle with sides or legs 2 and 4. The question wants to know the length of the hypotenuse in simple radical form. So that is x. So we'll do 2 squared plus 4 squared equals x squared. 4 plus 16 is x squared. 20 is x squared. Take the square root. X equals the square root of 20. And we want the simple radical form, so that breaks down to 4 times 5. So x is the square root of 4 times square root of 5. So therefore the final answer is 2 square root of 5. Problem number 10 is also an application of the Pythagorean Theorem. It says the sides of a rectangle are 8 and 15. How long is the diagonal? So I'm going to draw a rectangle. I'm going to label the sides 8 and 15, and from a previous chapter we know the opposite sides are congruent. The goal is to find the length of the diagonal, which is the blue line. I'll call that x. So 8 squared plus 15 squared equals x squared. 64 plus 225 equals x squared. Using my calculator and adding those up, I get 289 is x squared. So x is the square root of 289, which is 17, and I'll put my unit of centimeters. Should also probably put my unit in problem number 9, 2 square root of 5 inches. So the final answer to number 10 is 17 centimeters. The next learning target is to use the converse of the Pythagorean theorem to determine if a triangle is obtuse, right, or acute. So in class we learned if c squared was equal to a squared plus b squared, then the triangle is a right triangle. If c squared was greater than a squared plus b squared, then the triangle was obtuse. And the third case was if c squared was less than a squared plus b squared, then the triangle was an acute triangle. We do want to remember that c is always the largest side. So c is the largest side. And the other thing we needed to remember from a previous unit is the sum of the two smaller sides must be greater than the third side, or the largest side. Otherwise, you cannot make a triangle. So if we look at problem number 11, the 20 is the biggest side. 15 plus 18 is indeed bigger than 20, so a triangle exists. If I were to look at problem 12, 11 is the biggest side. 7 plus 8 is bigger than 11, so a triangle does exist. And if I look at problem 13, 13 is the largest side. 6 plus 7 is not bigger. So I'm going to draw that red line. Is not bigger than 13, so no triangle exists. This was a review from first semester. So if we go back to problem number 11, now that we know a triangle exists, we're going to do 20 squared. We're going to compare that to 15 squared plus 18 squared. When I do that on my calculator, the left side is 400. And when I do 15 squared plus 18 squared, I get 549. 400 is less than 549, so this is an acute triangle. When I look at problem number 12, I'm going to do 11 squared. I'm going to compare that to 7 squared plus 8 squared. 11 squared is 121. And when I use my calculator, 7 squared plus 8 squared is 113. 121 is bigger than 113. Therefore, this is an obtuse triangle. If you found those two values equal, it would be a right triangle. And for clarity, this is the work that I'm highlighting in yellow to determine if it is an acute triangle or an obtuse triangle. And you always want to validate that it is a triangle using the idea over here that the sum of the two smaller sides must be greater than the third that I just highlighted in pink. That's why I did the pink step in each of these problems. Let's take a look at the next learning target. So problem number 14 is a special 45-45-90 triangle. And we learned in a special 45-45-90 triangle that the two legs are always the same. So we in class wrote leg, leg, leg root 2. So if we look at problem number 14, this leg in green is the same as the other green leg, therefore AC is 14. The hypotenuse, which I'm highlighting in blue, is going to be 14 square root of 2. So for problem number 14, we're using the relationship that I drew in red. For problem number 15, we have a special 30-60-90 triangle. And I'm going to summarize the special 30-60-90 triangles here with this blue triangle. So here I'm drawing a special 30-60-90. In class, we call this green leg the hypotenuse. We called the yellow leg the short leg. And we called the pink leg here, which was across from the 60, we called that the long leg. So always across from the 60 is the long leg, always across from the 30 is the short leg, and always across from the 90 is the hypotenuse. And we learned 3 formulas, or actually 4 formulas for a 30-60-90. One formula we learned was that the short leg is equal to the hypotenuse over 2. The second formula we learned was the long leg was equal to the short leg times the square root of 3. And a third relationship, which is related to number 1, is 2 times the short leg is equal to the hypotenuse. So let's use these 3 relationships to solve problem number 15. If we look at number 15, we are given the side across from the 30, which is the short leg. So using this highlighted blue formula, 2 times the short leg is the hypotenuse. That means the hypotenuse here is 2 times 10, which is 20. So that's how I'm going to get the hypotenuse, 20. We know that the long leg is the short leg times root 3, and I'm highlighting that in yellow. So the side across from angle T, which is the 60, is going to be 10 square root of 3. Let's take a look at problem number 16. In problem number 16, we are given the hypotenuse. So using the yellow highlighted formula that the short leg is half of the hypotenuse, the short leg is here in yellow across from the 30, so that short leg is going to be 12 over 2, which is 6. We also learned that the long leg was the short leg times the square root of 3, which I'm highlighting in green. So therefore the green segment is going to be 6 square root of 3. For problem number 17, we learned in a 45-45-90 this yellow relationship. The 2 legs were equal, and the hypotenuse is the leg times the square root of 2. After we learned that relationship, we talked about, well, what if you're given the hypotenuse, and I'm highlighting here in blue, how do you find the legs? And the pattern that we saw in class using the Pythagorean Theorem is the leg was always the hypotenuse over 2 times the square root of 2 that I just highlighted in green. So in this particular problem, number 16, we are told the hypotenuse is 16. So to find each leg, we're going to use the formula below, hypotenuse over 2, square root of 2, and that reduces to 8 square root of 2. So the 2 legs are 8 square root of 2. Before we take a look at problem number 18, I want to take a look at problem number 19. In number 19, the 5 root 3 is the long leg, which is the short leg, square root of 3, if we look at the green highlighted formula. And I'll draw an arrow here so you see that. So if you compare this, that means the short leg is the number in front of the square root of 3. So that means the short leg, or y, is 5. So that's the short leg across from the 30. And to get the hypotenuse, we're going to use the pink formula that I'm highlighting. 2 times the short leg is the hypotenuse. So the hypotenuse is 2 times 5, which is 10. So now let's take a look at problem number 18. If you look at problem number 18, the 12 is the long leg. But notice it does not have the square root of 3 like problem number 19. In problem number 19, since we are told the long leg is 5 root 3, the short leg is the number in front of the root 3, or 5. In class, we learned if you don't have a square root of 3 on the long leg, the short leg, so this is the formula we learned, was equal to the long leg divided by 3 times the square root of 3. So using this formula, the long leg is 12 over 3, or excuse me, short leg is 12 over 3 times the square root of 3, and that simplifies to 4 square root of 3. So this blue segment, which is the short leg, is 4 square root of 3. Then using the pink formula at the top of the screen there, to find the hypotenuse, you double the short leg. So if you double 4 root 3, you get 8 root 3. Let's take a look at problem number 20. For number 20, it says, find the length of the diagonal of a square whose area is 64 inches squared. So I'm going to draw a square. And we know in a square all the sides are equal. We talked about in class that the area of a square is length times width. And all these sides are the same in a square. So that means the area, 64, is x times x, or 64 is equal to x squared. Taking the square root of both sides, x is the square root of 64, or 8. So all the sides of the square are 8. And your goal is to find the diagonal, which is this blue line. This is a 45, 45, 90 right triangle. Therefore, the diagonal, using the relationship leg, leg, leg root 2, is 8 square root of 2. Let's take a look at problem number 21. Find the length of the altitude of an equilateral triangle with sides 8. So I'm going to draw an equilateral triangle. I know all the sides are 8. From our class discussion, we know the angles are 60 degrees. The angle at the top is also 60, but I want to draw in this green line, which is the altitude, so that's what I'm trying to find. And the angles at the top of the triangle are each 30, because the 60 is split in half. And using this diagram, the bottom piece is also cut in half, so the green segment that I highlighted and the yellow segment are both 4. And if I focus in on the pink triangle, this is a 30, 60, 90 triangle. You can see that the hypotenuse is 8. The short leg is half the hypotenuse. Therefore, the side across from the 30, which is the long leg, or the altitude, remember the formula is short leg times the square root of 3. Therefore, the altitude is equal to 4 square root of